Hello, I'm Rhett Allain, and I'm going to talk about some of my favorite things in physics, modeling real world stuff using a lot of Python and other techniques. So, a couple of pointers to begin off with. My website, rhettallain.com. You can find most of the stuff that you want to see. Links will be there to other social media platforms, YouTube, and things like that. If you have questions, there's my email address, rhettallain@gmail.com. Let's go ahead and get started. I got to click. There we go. Okay, so I'm going to start off with a problem that we all know how to do most likely, but it's important to kind of look at some of the details in how we do this. And it's fine if you've seen this before. It's fine if you know it before. I'd rather do something that everyone has seen so that we can talk on the same level rather than do something that you have no idea what's going on. And this is a mass on a spring, classic physics problem. The first thing that we can do is to put this mass on a spring and let it hang vertically so that gravity pulls it down, and then mark the location of the mass with different, the location of the end of the spring with different masses on the end. So I've already done this. I put this on a board here, and we have this is the 0 grams on the end, and there's 20, there's 50, there's 100, and so forth. And if we can model this spring force as some constant times the stretch, then we could find out that spring constant. This equation, I'd like to point out, important that I don't have the negative sign because it's not a vector equation. A lot of people put that negative sign in there, but that's just up to you. So if we plot the spring force, which we can calculate as just the weight, because it's in equilibrium, as a function of the stretch in meters, we get this very nice linear function. And you can see that we can fit a line to that, and we can find the slope, and the slope of that line would be the spring constant. In this case, it's 5.33 newtons per meter. Okay, nothing fancy there. But what if I take that mass and I pull it down and let it go, and it oscillates up and down? So this is a 200 gram mass, and you could just use your stopwatch and time how long it takes for this to oscillate up and down. And I got 1.2 seconds for one oscillation. And so this is something that we want to model. This is simple harmonic motion, and we want to model this. Now there's a bunch of different ways we can do that. First, we can start with our Newton's second law equation right here. This says that in the y direction, so now we do have that negative sign because we're dealing with the y component. The y position, if I pick y equals 0 at the equilibrium point, would be equal to mass times acceleration. And I'm ignoring gravity in this case. If you want to add gravity, it gets a little bit more complicated. But let's just assume that we don't have to worry about that. So this is our differential equation that we want to solve, and we can write the acceleration as the second derivative of position with respect to time. So now we have that. So how do we solve that differential equation? It's a differential. We could just use our normal differential equations methods, right? If you take differential equations, the whole point of the course is to look at different ways to solve that equation. We could also just look it up. You could say, and this is what they do in the introductory physics course. If you haven't had differential equations, they just say, well, here's the solution. You could also try guessing the solution. But I want to show you one method to solve this differential equation that maybe you've used before, that I find very useful, and we're going to use a lot of this stuff for the rest of the talk. And that's to break this motion of the mass into small intervals of time, tiny steps. Breaking problems into tiny steps and making assumptions during each step. This is the whole idea behind a numerical calculation. Okay, so I do this a lot, and it's a great way to practice stuff, and the tools are very accessible now, so I'm going to show you how to do a numerical calculation. And again, maybe you know how to do this, maybe you might see something new, maybe it's all old, but we'll do some fun stuff with it too. I just want to make sure that we're all on the same page. So the first thing that we need to do for this motion is to break it into small steps. So in this case, I just pick a time interval of delta t of 0.01 seconds. So small is relative depending on what you're doing, but in this case, 0.01 seconds should work fine. Now, during that small time interval, I'm going to calculate the spring force. So the spring force in this case depends on the value of y. K is constant, but I need to know my y value, and I can calculate my spring force. Now for the magic. During that 0.01 seconds, if the mass is moving, the momentum changes and the position changes and the force changes, everything changes. But if I assume that the net force is constant, then I can use that net force to and the momentum at the beginning of the time interval, P1, I'm calling that P1, to find the momentum at the end of the time interval. So this is wrong, but it's only kind of wrong. If delta t is small enough, it's good enough. And this is one of the important parts about the numerical calculation, assuming that that's true. And it's very, very powerful, and we can use this in lots of different situations. But after that, I can assume that the momentum is constant, and say momentum over mass is the velocity, and I can use that to update the position. So here we're calculating the force, we are updating the momentum, we're updating the position, and then we're just going to do it all over again for the next time interval. And it's such a simple idea. It's just that if I want to model this for 1 whole second of time, it would take 100 of these loops, right? And I don't want to do that. And so instead, I'm going to do this in Python. This is the whole program here. This is the whole program to model the motion of a mass on a spring. I'm using WebVPython, so it's online. You don't have to install anything. Students don't have to install anything. I really like this. It's something that came about maybe 10 years ago, and it made a huge difference education-wise, because we don't have to worry about how students access the stuff. They don't have to buy anything. They don't have to install anything. And those barriers may seem trivial, but they can make a big difference for students. Okay, let's go over this code really quick. These lines just make the graph. Graphing, this is WebVPython, so it has built-in modules for graphing and 3D stuff, and we'll see that later. But this is just to make the graph. F1 is the function I'm going to plot. Now here are all my constants, the mass, the initial y position, the spring constant, the initial velocity, and I did this in terms of velocity instead of momentum, but I think you can see that fine. And I am including the gravitational force and the initial time and the initial time step. So with that, what I do is here I just do a loop for 3 seconds, and I go through and do the same thing every time. And I calculate the force, and that's the total force right there, right? That includes gravity. I use that to calculate the acceleration, update the velocity, update the position, update time, and plot it. And that's what you get. And, it's amazing to me that we get this. We know that's the solution. We know it should be a trig function, and that definitely looks like a trig function. And the code is so simple. So I always find this amazing, and I love it. Okay, but we can also make a 3D model of this. I'm not going to go into all of the details, but WebVPython allows us to make these 3D animations like this. So, and this is just, it doesn't actually stop. I accidentally stopped it. This is an animation. So here's a mass on a spring oscillating up and down. It's the same situation that I had before. And for me, I mean, that's a pretty cool thing, right? Because I can recreate reality in this virtual environment very simply. The code here is not too crazy. And it agrees. It's what we saw. But wait, it gets even better. What if I took that mass, and instead of letting it move up and down, I let it move in 3 dimensions? Well, with just a slight change to the code, but the same idea, I can do this. This is a 3-dimensional mass, and I'm going to rotate the environment around. This is in WebVPython. Okay, so not too difficult to do. And this shows the power of numerical calculations. It allows us to do things that, yes, you could do this analytically, but students in an introductory level can do this very easily, right? Because if they understand the 1-dimensional case, going to the 3-dimensional case is basically the same thing with just different initial conditions. And I think that's cool. Okay, so I'm in love with WebVPython. I'm in love with Python and numerical calculations. I do want to point out the following. A lot of times people say there's experimental physics, there's computational physics, and there's theoretical physics. But really, we don't have a difference between computational and numerical physics or theoretical physics. They're really all the same thing. It's all about building a model. I can model a mass on a spring with a cosine function. I could also model a mass on a spring with a numerical calculation in Python. Okay, so the building of the models is theoretical physics, whether it's in Python or whether it's in paper or whatever. That's a model. Building a model is theoretical physics. Testing the model is experimental physics. So when I take that mass on a spring and I let it oscillate up and down and I record the time, I'm getting real data. I'm making my model and I'm seeing if it agrees with the real world. So those are the two things that we do in science. And a lot of times we get confused and we try to make it more complicated, but science is about building models and seeing if they agree with real life. Okay. And so, like I said, computational is not an experimental physics. And a lot of people might say that at some point. They say, oh, well, I don't know what the computational model is going to give me, so when I run it and I change the variables, I'm doing an experiment. But it's not real. It's not real life, right? It's whatever you want it to be. You made the model. You want to see if it agrees with real life. Okay, so computational physics, computational calculations is theoretical. And, I think even theoretical calculations like the simple harmonic oscillator, those are still computational. What we do is we get an analytical solution for something like this, and then that's great. But what we've done is reduce the problem into these other special functions, cosine and sine. But if I have cosine of 0.2, how do I get the cosine of 0.2? I have to look it up in a chart or do a computational experiment. So we just reduced it to other computational problems. So cosine and sine are still computational problems. That's just me. That's just what I think about it. Okay. So I know people do numerical stuff in other environments. What's so great about Python for me, it runs on everything. It runs on Mac, PC, Linux. It runs on your phone. I think that's amazing. There's online versions, so students don't have to install anything. The code is simple, right? I don't have to declare variables. I don't have to say what kind of type it is, which is a problem. I agree. It's not the best, but we're trying to learn physics. We're not trying to learn programming. Smartphones, I already said that. The graphing in there is so easy. Animated graphs in WebVPython is super easy. I've done animated graphs in Python with Matplotlib. It's still nice. It makes really pretty graphs, but whatever. We have the ability to use 3D objects like the sphere and the spring and all that stuff. It has built-in stuff for vectors, and of course it's free. Mathematica's nice. MATLAB's nice, and even if they are free for our students while they're here, once they graduate, it's not free. So, and then this is something else I like. It's named after Monty Python, that show from, I guess, late 70s. I don't even know what that was, but I think that's just funny, right? It's funny. There are different versions of WebVPython. This is the full Python version, so you could install Jupyter notebooks, and you'd have to install the VPython module and then load the VPython module. But that allows you to use other modules like NumPy and whatever you want along with WebVPython. It's not the best. I don't do that for students unless I have to, unless you want to do matrix problems or something like that. This is another really great option. This is Google Colab. You can use essentially Jupyter notebooks online without having to install anything. I love this because if a student is using a phone or a tablet, it's harder to install Python, but they don't have to. They can choose a web page. This is GlowScript. GlowScript is the original web version of VPython. You just log into it and you can code it. I like this one that I normally use. It's a web VPython at trinket.io. I like this because you can see the code and the output right next to each other. I can share it with students and they don't even need to log in to edit it. They just can't save it. So I really like that. But that's just what I do. Okay, so that's my introduction to numerical calculations with Python. Now let's use it to do something with the real world. Remember, the title of the talk was stuff about the real world. So we got to do real world things. This is a graph of something that you may have seen before, and this is actually from a paper from the European Journal of Physics looking at human sprinters. Okay, so if I have this is actually data for Usain Bolt, who's very, very fast. We have over here a plot of position versus time, and I think it's easier to look at the velocity as a function of time. So a human starts running, they increase in speed, but they don't keep increasing in speed forever. They reach some constant speed, and then sometimes they even slow down depending on how far it is because they just get tired. And so the question is, how do we model this? How do we make a model of a human running? And that's what we're going to do. So this is, I like to, this is an older video, but I like to use my own kids for demonstrations because I pay for their food and stuff. So here's one of my kids running, and we can see in this model of him running, there's a couple of important points that we need in our model. Number one, they accelerate and they reach a constant speed. We need to account for that. And then number two, the difference between running and like Olympic speed walking is that when you run, both feet are off the ground at the same time. So we're doing both feet off the ground. So you're really jumping in the air a little bit. One of the common things I see is that it has to do with air drag. And it can't be, right? Because here's a person jumping out of a plane. There's a downward gravitational force, and it's not negative because the negative's in the y component of the gravitational field. And then there's the upward pushing air resistance force that depends on the density of air, rho. It depends on the cross-sectional area, A, the shape, C, the velocity squared, and the v hat's a unit vector, so that's why I have a negative. And if you jump out, you're going to increase in speed until these two forces are the same, and that gives a terminal velocity of about 54 meters per second. Now, if you're running and you have air resistance, so there you're running, you would have, at a constant speed, you could say there's a backwards pushing air force and a forwards pushing friction force. But if we could calculate the friction force depending on the coefficient. The shape of a human running is different than the shape of a skydiver, but we're on the same ballpark there. It just seems like you would be able to run a lot faster if it was air resistance, right? Because free fall is 54 meters per second. That's really fast. And then we also have the problem I like to bring up is the treadmill. If you have a human running on a treadmill, they can't go infinitely fast, and there's no air pushing against them. Yeah, maybe there's some air pushing against their legs, but it seems like humans run about the same speed on a treadmill as not a treadmill. So I don't think it's air. Air does affect it a little bit, but I don't think it's mainly air drag. Another thing that people come up with is power. They say, well, a human outputs a constant power, and so at that point, the drag and the power are bound. All the power from the human goes into the drag against the air, but it's still an air resistance argument, and I don't really like that. And I don't know that I'm right. I just like to play around with physics. Okay, so let's build a running model. And in this model, we can imagine that a human is like a ball moving and bouncing along the ground. And there's a couple of important points. While that ball is in the air, the human ball, you have 1 foot forward and 1 foot back, and you need to be in the air long enough so that your two legs can switch positions, right? Because that's what you do. I don't know if you've run before, but you might want to go try it. 1 foot goes forward, 1 goes back, and you switch in the air. Okay. So you have to have enough time to do that. Also, the human can only exert a constant magnitude force with the ground. And now that means that they can push up and forward. So, but the combination of the total contact force is, the maximum force is constant. And finally, the ground contact time depends on the speed. So the slower you're running, you're in contact, your feet are in contact with the ground for a longer time than when you're running fast. So there's that relationship. So if we model this as a ball, it looks like this. So here's my ball. It comes in, it hits on the ground, the human ball, and it goes back up. And the important point is that this F push is constant, right? So if I push all the way in the X direction, then I won't go off the ground. If I push all the way in the Y direction, it just gets pushed up. And it may have already be moving, and that's fine. So at the point of constant speed, you're not speeding up anymore. There'd be no more forward pushing force. It's just pushing up. Okay, that's the model. And it's just a model. And then we have the momentum principle. I don't even remember why it's there. Okay. So this is based on real data. So here's some real data. And here's the article from the Journal of Applied Physiology. So a couple of things that you can get from experimental data. Number one, a human, when they impact with the ground, they can push on the ground, and so the ground can push on them with a force between 3 and 4 times their weight. So we have to pick. It depends on the person. Everyone's different, right? But it depends on the person. So max weight between 3 and 4 times, max force between 3 and 4 times. The time it takes a human to switch feet also it depends on the person, but it's about 0.3 seconds. And finally, the contact time. This is what this graph shows. This shows the contact time between the person's feet and the ground. And this is experimental data, right? So what they did is they had a person running with different speeds, and they had a little force plate that the person pushed on. And then they could record how long was the person in contact with the ground, what was the person's speed. And these are different people, but you can see that as they go faster, this is speed, and this is the contact time. The contact time decreases with increased speed. Now, what's the function for that? It depends. But this, and again, this is an experimental model. So we have all the things that we need. We have to pick some constants. But we have all the things we need to build this numerical model of running. I have a ball. I can do that. I can calculate the gravitational force. I can calculate the pushing force. And then I can just change the angle. I need to change the angle of that contact force such that they're in the air for a long enough time that their feet can switch. You need to be that 0.3 seconds in the air. And the problem is, as I go faster, that same force, not only I have to push more and more up in order to get up higher because it's only applied for a short amount. It's applied for a short amount of time. Well, I'm going to skip a lot of the details, but I will show you the model. Here is my running model in Web v Python, and you can see the ball bouncing along the ground. That's a human, and it's going faster and faster, but it doesn't keep increasing in speed. And if we plot the velocity versus time, I get this. And so you'll notice these little steps. That's because while the person's in contact with the ground, they increase in speed, but while they're in the air, they don't increase in speed. Increase, don't increase. So these are the times they're in contact. And then up here, they're not increasing in speed because their whole contact force is just needed to push them up to get them in the air long enough to switch their feet. And I like this running model better because it doesn't depend on air resistance, which like I said, I don't think that's a good thing. Okay. When you build a model, the best part of building a model is using it for things that you can't normally do, right? If this agrees with Usain Bolt, now I can say, what if I put Usain Bolt in a situation that I couldn't easily replicate? And I would like to use this for running on the moon. What would it be like to run on the moon? Because the moon, yes, it doesn't have air, but it has a lower gravitational force, and that's really it. What would happen if you decrease the gravitational force? Could you run faster? Could you run the same? What would happen? The first thing that we need to do is to think about what would happen with the lower gravitational field. Could you jump? You could definitely jump higher. Right here we see an astronaut on the moon jumping. And then I have here a human, again, one of my children from a while ago, jumping. And the gravitational field is different. It definitely looks different. So one of the things that we can do to model a jump on the moon, if we can do a jump, we can do running, is to assume that both jumpers have the same mass and they push over the same distance. So imagine I'm jumping on the moon and I squat and I extend my legs over a distance of, 0.3 meters with the same force, whether the gravitational field is 1/6 or g, it doesn't matter. And then we can model that. So here's what those two models look like. Here, this is a moon. Yeah, put a little spacesuit around the sphere, right? Because the sphere needs a spacesuit. And then here's a person on the Earth, and there's blue because it's air. So, and I did do this in VPython, Web VPython. And then if I plot those two jumps right here, you can see they both have parabolas. They have different accelerations, but it seems to be okay. And I'm not sure that's how you would jump on the moon, but that's fine. But now if I model a runner on the moon, what would change? Well, now I don't need as much force pushing up so that they're in the air for a long enough time to switch legs. And I haven't taken into account any spacesuit stuff, so let's just assume they're in a space, what would that be called? A space city on Earth, on the moon, so they don't have to wear a spacesuit. So they don't have to push up as hard. So that means they can spend more of their motion moving forward, pushing them forward and speeding up. So they should be able to run faster on the moon. So if we apply that, all I have to do in my numerical model that I built before is change the gravitational field, change the value of g, and let it go, right? So if I do that, this is what I get. So on Earth, in this model, I get a maximum speed of about 10 meters per second. On the moon, during that same time interval, it didn't slow down. It got to 15 meters per second and kept speeding up. So you could easily go greater than 15 meters per second. That's really fast, okay? That's really fast. And again, assuming there's no spacesuit. But I want to tell you something that you may not know. People have actually run on the moon, and we have video of it, and this is what it looks like. And there's a couple of issues here. One, they're wearing these spacesuits, so it's not easy to bend your legs and so forth. It's easier to get into the air and switch your feet, and so humans actually kind of modify the way they run and fall over even there. So you can adapt the way you run. You don't have to run the same way on the moon that you would on Earth. You could, but you don't have to. So that's something that's kind of fun to look at. And this is something that I found too, that I found amazing. There was a NASA study that looked at how would you run on the moon and how would you run in different gravitational environments. So right here, there's a guy running on Earth, no surprise there. Right here on the right side, what they did was they took he's running sideways and he's suspended by a harness. So he's actually on an angle and it makes an effective gravitational field because he gets pulled back into this wall, but he's running sideways. And so these cables are supporting different parts of his body. And you'll notice that he is running a lot different. Look how far forward he leans. That shows that he's increasing his speed. These videos are amazing to look at, and I just love them. And I would love to see someone actually run on the moon. But if you did run on the moon, there is something else you need to consider. Turning, okay? Because if you're running on the moon and you're going faster because you have more time to switch your legs, you also have a lower gravitational force, which means you have a lower normal force on impact, which means you have a lower frictional force. And now you need to turn. When you turn from that friction force between your feet. It's going to be a lot harder to turn due to the lower gravity and the greater speed. So if you were running on the moon, I would just say be careful, right? Because you don't want to get yourself running on the moon where you're in a situation where you can't turn in time and you crash and all sorts of stuff. I'll have to say though, I was inspired by the book Artemis. What was his name? Andy Weir, and he wrote The Martian. He wrote Artemis. He wrote the Hail Mary Project. I really enjoyed those books. And one of the things on there is they have a moon base. And they are running, and they talk about turning, and that's what I was like, oh, what would it really be like? So I wanted to model that. So that's not real because it's from a science fiction book, but I said real stuff. And the astronauts running on the moon, that's real. Okay. Let's look at another real situation that is amazing to imagine, and this is not a real picture. This is the Mars helicopter. So I want to look at how can we model something like a helicopter. And once we model a helicopter, I could say, what would it be like on Mars? Could you have a human-powered helicopter, which there is? How hard would that be? All those things that we can do. So this is the the Mars helicopter that's on Mars right now, and it can fly. So let's look at modeling a helicopter. So here's your basic helicopter. I drew this, so we have a downward gravitational force, and then the rotors rotate in a way to have an upwards pushing air force on the helicopter. If it's hovering, then these two forces have to be equal in the y direction. The air pushing up, gravity pushing down has to be equal to 0. So those two are equal. And then you can think about, what does the tail rotor do? Because it does do something. And in fact, the hint is the Mars helicopter does not have a tail rotor. It has to do with frictional torque from the rotors would cause it to rotate, and so the tail rotor just prevents it from rotating. This has two counter-rotating props so that the net torque is 0. So that's just for fun. Okay, let's model the forces on a hovering helicopter. Imagine that this helicopter just takes a cylinder of air that's the same size as the rotors and throws it down. And that throwing down stuff is what's going to cause the air force pushing up. So this cylinder of air has a cross-sectional area of A. It has a height of h, and it's moving down with the velocity v. And so if I find the force that the helicopter pushes on that air, that's the force that the air pushes on the helicopter. So that's the force that we want. So that's that upwards pushing air force is that. And we can find the air force by looking at the change in momentum of this air. So that air started up here, and then it gets pushed down, so it has some velocity. And if I can find the change in momentum and the change in time, I can get the air force. And so the momentum of that air is just the mass of this air times the velocity of the air. I'm calling it v. And then the mass of this air is the density of air, rho, times the volume of that cylinder, which is just the height times a. So the change in momentum of the air is rho ah, which is the mass, v, and then it started at rest, so it's 0. So that's what we have. Now I have the change in momentum, but I don't have the time. So let's imagine the time it takes for that air to go down. It starts up here at rest, and then ends up down here at going a velocity v, and it travels a distance h. Right, I moved it down below that, but so I know the distance. The average velocity is the initial velocity plus the final over 2, so v over 2, and the distance traveled is h. The time interval is delta t, so I can solve for delta t. 2h over v, and that v is the velocity of the air, the final velocity. If I put that into my air force equation, I have the mass rho ah, velocity squared, because I had a velocity in the time and I had a velocity already there, and then I have a 2 from over here, and I have an h, and the h is canceled. This is what we want in physics, right? We want to pick some parameter h, which really shouldn't matter because it's always throwing down air, and we just stick with it and we hope things work out for the best. In this case, they do. That the height of the air column cancels, and I'm pretty happy. And then if it's hovering, then this must be true. This has to be equal to the weight. So this is my equation for hovering, and I covered up with my picture. Sorry about that, but it says hovering. It doesn't say hove. Okay, so I'm pretty happy about that. One of the things that I want to find is the power, right? Because I want to look at like a human-powered helicopter. How hard would it be to do that? So for power, I'm going to start with my column of air with 0 velocity, and it's going to move down here, and I can calculate power as the change in energy per time. And in this case, let's just say it just has a change in kinetic energy. So if I know the initial kinetic energy of 0, the final kinetic energy of 1/2 mv squared, kinetic energy right there. If I put that in for power, I put that in for my energy, I have an expression for time already, right, dependent on h. And you'll notice here, this mass depends on h. I have the 1/2. I had a 2 already from right there. Where'd that 2 come from? Oh, that came from mv cubed, right? Because 1/2 mv That's the time. That came from the time. I used my delta t right there, and that's why I got a v cubed, and that's where the other 2 came from. And then if I put in for the mass, that h cancels again. So that's good. We shouldn't depend on the mass. On the height. It does depend on the mass. If you solve this for velocity, you get that. And that was the velocity I had from before. I'm sorry. I got ahead of myself. And I could put this into that velocity to get the power. And I'm not going to do that because then you have a 3/2 power thing in there, and I didn't want to deal with that. But the important thing is, notice up here, the velocity depends on the mass and the area, right? So if you have a larger area, did my thing freeze? No, just my video did. That's weird. Well, just pretend like I still have a video there. It'll be fine. That's fine. You don't need me. I'm freeze and sneeze mode, but hopefully you can still hear me. If I have a larger rotor area, I have to push down air with a lower velocity, right? And then a higher area, a larger area, a smaller area would have to be a higher velocity. Okay, so area of the rotors does indeed matter. What does this do? Is that still working? What if I change that? I just kind of, when things don't work, it just kind of bothers you a little bit, but oh well. I could try laptop screen. No. Okay, there. I had switch cameras. Ha. Why did that not work? I don't know. Okay. So, power. That's where we're. Power. Here is a human-powered helicopter. You'll notice this person in the middle here pedaling away, and these giant rotors. And so this was part of was a Sikorsky Prize, and the goal was to create a human-powered helicopter that could fly for 3 minutes and stay in a certain height and so forth. And this one didn't win. This particular run didn't win. But you'll notice how exhausted that guy is. He was really pedaling for all that he could. And so again, the velocity of the air depends. Remember, the power depends on velocity cubed. So you want that velocity as low as possible, and that means make as large of a rotor size as you could. So those are really large rotors. And there's your power. Well, one of the things that before we go on to calculating the actual power of this, it's important to realize this. Helicopters are real, right? We know how that they actually fly. And I saw that helicopter taken off, so I got a video of it. And you can look up a bunch of helicopters on Wikipedia. You can look up their rotor size, you can look up their mass, you can look up their engine power. So we have all this data to check and see if that model is even legit. I didn't think it'd be legitimate, but if I plot the calculated power versus the listed power for a bunch of helicopters, you can see that I get a really, really nice fit. So that model, even though it seems like helicopters are way more complicated than throwing down air, the model works fairly well. If I plot the airspeed calculated for hovering as a function of mass of the helicopter, I get this. And so this says that there's really no huge relationship between the air that gets thrown down and the mass of the helicopter, but you do see that there's some maximum of 32, 31 meters per second and a minimum of 15. So we have some range that makes sense. So let's use these values for power and go back to the human-powered helicopter and just make some calculations. So just as a picture, there is an actual commercial airliner. That's the Gamera 2. This is the Gamera 2 from the University of Maryland. Here's some 2 real helicopters, just so you can see how big it is. It's big. The mass listed from the website was 32 kilograms. The human was 60 kilograms. We have the total. The rotor radius, we have that. We can calculate the area. I calculated the thrust speed just for fun, 1.68 meters per second. And this gives a power to fly of 755 watts. I don't know how much you are into exercise, but I'll tell you, That's huge. Okay. This is a plot from this is the Bicycling Science by David Wilson. There's this graph right here there's a similar one on NASA's website too, of human power output as a function of time. So this is where most of us are right here. And you'll notice that as we exercise for longer times, our power decreases. This is a nonlinear scale here. So this is duration and this is power. So if you exercise for, 1 hour, you can get like 100 watts or something like that. Very high performance athletes are way over here. So they curve out a bit. So if you do very, very short amount of times, you can get extremely high power. This graph goes up to 300 watts. So that's that. Let's look at the Mars helicopter. So it has a mass. The Mars is different, right? Because we have a lower gravitational field and we have a lower density of the atmosphere. So, it's kind of, how do you make that fly? That's the mass of the whole, that's the gravitational field on Mars. It's 38%. The density of air is 1% of on Earth. The mass of the helicopter is 1 kilogram. NASA lists its power at 200 watts. But if you do the same calculation with the total energy, the total helicopter power, I got 373 watts. So again, it's just a rough estimate. But it's fun to see these things add up. I think this average power was the solar power, was calculating the solar power that hits the thing. I don't remember what I was doing. I'm not sure what that average power is. That's the power in the battery. That's the iPhone battery. The thrust speed, 200 meters per second. So it's a lot harder to fly on Mars. Oh, and there's a link to the calculations if you really want that. Now, again, I like to expand things into stuff that's not real. This is, I'm a fan of superheroes. This is from the first Avengers movie. This is the helicarrier. It's basically an aircraft carrier that can fly. Well, it's a helicopter, so we can use the same idea. And in this case, it looks like a Nimitz-class carrier, which I know the size of. You can look up the size of that. Once you know that, I can measure the radius of these rotors, 17.8 meter radius for each one of those. And from that, I know the mass, I know the area, I know the density of air. I can calculate the thrust speed. That's really high, 642 meters per second. And if you use that to calculate the power, 3 times 10 to the 11th watts. That's really high. Just for comparison, the nuclear power plant on an aircraft carrier is around 2 times 10 to the 9th watts, so way, way higher. And it's not real, right? It's a superhero movie. We don't do it. We don't look at this stuff because we know they're real. We look at it because we know they're fake. That's what makes it fun. Okay. But for me, I wanna fix things. So let's say that we fix the helicarrier. And the problem is the airspeed, right? If I have a thrust speed of 600 meters per second, that's too fast. Let's decrease that to something fast but manageable. So if I want to decrease the thrust speed to 50 meters per second, then I need to increase the rotor area. So if I increase the rotor area, it would be 6.5 times 10 to the 5th meter squared. What would that look like? Well, you know what? I drew it for you. Here's my new Shield helicarrier. There are the new rotors. That's how big they would be. So it'd be huge. I like to think a lot of myself because that's what I do. This is the helicarrier the next time we see it in the Marvel Cinematic Universe. And you'll notice that it looks different, right? I claim, and I'm not sure that I'm right, that they said, oh, well, yeah, the airspeed should be going a lot faster, so they changed it to these thruster things. And I pretend like I did that, but I didn't really do that. So that's just for fun. Okay, let's look at one more real-world application with physics, and that's how to catch a baseball without physics, right? And this is one of those things that's really crazy. Anytime you catch a ball, humans catch balls all the time. But if you wanted to calculate how to catch a ball, wow. I mean, you can't do that in 3 seconds. So here's the physics problem we have. A ball is launched, and the human wants to catch it. So this ball has some initial velocity at some initial angle, and it's going to go without air resistance for now, and it lands over here. So this person needs to calculate where it's going to land, and then they need to move to that location. And they need to do that all in the time that that the ball's in the air, or you won't catch it. So here's your basic projectile motion problem. The ball is launched with initial velocity. We can break that to x and y components. There's the y velocity. There's the x velocity. And then I tell my students, break it into an x motion and a y motion. In the x direction, we have an initial position. We don't know the final position. We can use the kinematic equation for zero acceleration. And then we can look at the y motion. We know both the initial and the final position in the y direction. It lands back at the same place. We have this kinematic equation, and we can solve that for the time. And then we can use that time in this x equation right there, and we get that. And that's the range equation, which, please don't just look up the range equation. I have my students, they just use the range equation in situations where you can't do it. So suppose that we model this in VPython, because you know that's what I'm going to do, model it. Here's our ball, baseball launched. There's our player, and there's the grass. And so the person could run up to the place where it's going to get caught and then catch it. And that doesn't normally happen, okay? But that's how you do it if you did it with physics. You'd calculate the location, and then you'd run to that location. Forget about all the problems with actually measuring that location. There's another way to catch a ball. So it depends on this thing called the apparent position. So imagine that you see the ball in the air and you you look at the ball and you look at where it lines up with the meter stick, right? That's one way to consider the apparent position, because we see things kind of flat, right? It looks like it's at that position. So we can use that. What would it look like if I launch a ball and I just look at the angular position, the parent position, as a function of time? So let's look at some situations. So here is a ball launched, and we're going to look at the parent position. So here's the person. They're measuring the parent position for that ball. So it's short. And you can see what that AY is, a parent Y position. So it looks like it comes up and then it comes back down. Okay, here's another one. This one's going to go over the person. So we have a problem with the Y position. It was an infinite, right? And then it was not an infinite. So you get this little jump, but that's fine. That's fine. And then what would it look like? And these curves are important. I'll show you these in a second. What would it look like if the person caught the ball? So they're already in the right position. Landed right at the person, and look at that. What would you say about the y value as a function of time there? It has a constant apparent velocity. And if you put all those graphs together at the same time, here's the ball that went too long, here's the ball that went too short, and here's the one that caught just right. So that tells us how to catch a baseball. You don't need to do calculations. One, look at the ball. In your mind, determine the apparent velocity, right? And we can do that. We can judge velocities, right? And then you want to set your motion moving forward or backwards. This is how I do it in Python. Set the human acceleration times something times the apparent acceleration, because I want them to be matched. I want to move the person in a way that the apparent velocity is constant. And in Python, I just keep doing that over and over. When you catch a ball, you just do it in your mind. You're just moving in a way such that the parent motion is constant. And that's how you can catch it. You don't need to do any calculations. So let's try this in Python. I'm going to have my little Python model that follows these rules. The acceleration depends on the parent acceleration. So if the ball is moving at a constant apparent velocity, this is 0, and they're not moving at a constant velocity either, so it's all good. So here is a ball launched with no air resistance. There it goes. And there's the person moving. See, the person's moving. And you'll notice they look a lot different than the other way. The other way, they move to the spot and waited for the ball to come there. But they don't do that in this case. Them moving helps them judge that the parent velocity is constant, and they caught the ball. And then, so there's that trinket thing right there. That was a website. Okay, so that's that. I'm leaving some time for questions. That's what I would normally do. One of the things I want to point out, and this is just a random infrared video of a train because I think it's cool, and I don't like to have blank pages. But the thing I like to say is that you can't really understand something unless you can model it, right? If you can build a model of it and reproduce it, that's how we judge real understanding. And so anything in the real world, if you can model it, then you have a good opportunity to understand that. So thank you very much for your time. Thank you for inviting me. I had a good time. I had fun talking about this, and thank you for paying attention. And that is the end, and I will say goodbye.